Hey guys, in this video tutorial we'll be solving the balanced binary tree problem on LeetCode. So when given a binary tree, we need to determine if it's height balanced or not, and they've given the definition of height balanced binary tree as it's a tree in which the left and right subtrees of every node differ in height by no more than 1. So first in this video we'll be solving this by a naive approach, and in the next video we'll be looking at a more optimized approach using depth first search. So what we'll do in this naive approach is that we'll go through each of the nodes in the binary tree, and then we'll check if that particular subtree on that node, if it's height balanced or not. So basically the difference between the height of its left subtree and its right subtree has to be less than or equal to 1. So first we'll write a simple height routine. Int height of tree node star. So this will just take the root node, and if it is not null, we'll take two variables x and y, and we'll recursively call this function on the left subtree as well as the right subtree. And then we'll return the maximum of these plus 1, and in the base case we'll just return a 0. So for the balanced function, the base case should be that if the root is a null pointer, then also we need to return a true, right? Because even an empty tree is a balanced binary tree, and that's also shown in this example right over here. So if the root is empty, we need to return a true. So if root is null, we return true. Then in the main case, we'll recursively call this function on its left subtree and its right subtree, and we'll check for this node as well. So we return the absolute difference between the height of its left subtree and its right subtree is less than 1, and then we'll have two recursive calls over here. Alright, so this should work. Let me just check the code once. So yeah, if root is null, we return a true, and then we check for this current tree, and then we recursively call the same function on the left subtree and the right subtree. Right, so let's give this a run. Okay, so this does work. Let's try this for one more test case. Okay, so this should work. Let's submit. Great. But you know, as you can see, the time complexity isn't that great. It's only faster than the 55.86% of the submissions. So let's analyze this a little bit. So what should be the average case time complexity? Let's say that the tree is balanced. So a balanced tree has log n levels, right? Where n is the number of nodes, and we're going through each of the nodes. So the average case time complexity of this algorithm should be order of n log n. But let's say the tree is not balanced, and in the worst case, it's kind of like a linked list. It's a skewed tree, and then we'll have to go through all the n nodes n times, right? So then the time complexity would be, in the worst case, order of n square. So this was it for this video. In the next video, we'll try a more optimized approach using depth first search to solve this problem. Thanks for watching.